Hello, in this video I'm going to show you how to create and sonify chaotic attractors using MSP. Chaotic attractors are a set of rules for the movements of particles and the resulting patterns from it. They are really interesting because when we zoom in, they are moving in a completely unpredictable manner. However, when we zoom out, there are some beautiful and interesting patterns that emerge. We can use these, we can turn these into signals in MSP in order to generate sound and modify sound in new, exciting, and unpredictable ways. Let's see how this is done. Alright, here we are looking at an empty MSP patch. Well, it's not so empty because we do have this little mathematical formula here, and this is the formula that we are going to use in order to simulate a chaotic attractor and generate our chaotic signals. You might recognize this formula if you have seen my previous video on visualizing chaotic attractors. If not, no worries, because now I want to talk a bit about what attractors are and what this formula exactly means. As you might know, attractor refers to two things. First of all, it's a set of rules for particles that are moving in a space with a given number of dimensions, so a 2D space or a 3D space, and it's also the patterns that emerge from that movement. Now, we are specifically interested in chaotic attractors because they exhibit chaotic behavior, meaning that depending on the initial position of the particle, we are going to get completely different movements. Each particle is going to move in an unpredictable, chaotic manner. However, when we zoom out, we are going to encounter these greater macro level forms and patterns that emerge from the movements of those particles. That is something I find really interesting. The fact that we can zoom in and look at the chaotic movements of these particles, but when we zoom out, we see these beautiful and interesting patterns emerge. Now, to work with chaotic attractors, we have to figure out what this formula exactly is. And you will notice that this formula does not have any numbers in it. That is because it is a very cool mathematical formula, and all cool mathematical formulas have exclusively letters in them. So let's figure out what these letters mean. First of all, this sign means a sine function. It's a trigonometric function. If you know what it is, great. If you don't know what it is an object in MSP that is going to take in a value and is going to give out another value. In this case, sine y means the sine of y. So we use a sine object and we give y as an input and we take the output of that operation. The same with sine z and sine x. X, y, and z refer to the current position of our particle in 3D Cartesian coordinates. So there's an x position, a y position, and a z position. There is an x coordinate, a y coordinate, and a z coordinate. dx refers to delta x. This is going to be the result of our calculation. dx, dy, and dz are the deltas, the movement that is going to occur on that specific given axis. How much we are going to move on the x-axis, how much we are going to move on the y-axis, and how much we are going to move on the z-axis. Since these define delta movements, we have to take the current position of our particle and add these values to them to calculate the next position of our particle. This dt is standing for delta time, I believe, and it is essentially the speed of our simulation. We are going to define this as a parameter, and we are going to increase or decrease it to play with the speed of our attractor. Finally, this b is an arbitrary value. Well, there is some history behind it that is not really important right now. All you have to know is that this is a constant and that this equals to 0.19 initially, according to this web page, which I'm going to put in the video description, of course. This constant, or this constant parameter, is something we can change down the line to generate different kinds of parameters and mess with the resulting pattern a bit. Okay, so knowing all this, I believe we can go back into Max, and again, we have the formula here as well, and see how we can implement this in the realm of signals. So let's start by creating an easy DAC. We are not going to hear anything first. We are actually going to visualize the audio signal before we start trying to hear it, but we need to turn this on for the audio processing to take effect. Secondly, we are going to work on a sample by sample basis. So on each sample, we are going to calculate the next position of our imaginary particle. This is surprisingly, or maybe unsurprisingly for you, difficult to do in regular max MSP. With the regular standard MSP objects, things are not going to be calculated sample by sample, but they're going to be using something that is called signal vector. So a bunch of samples are going to be processed all together to save on some CPU power. However, in this case, we do want to do discrete operations on each sample, and for this reason we are going to use gen tilde. We are going to define an algorithm here, and when an audio signal goes in or goes out, each sample is going to go through the algorithm that we define in this object. All right, now here's the thing though. Signals in general are one-dimensional, right? They go from, I don't know, minus something to plus something, and we cannot really add 2D or 3D motion in an audio signal. So what I am going to do is I'm going to think of this as 3 discrete or 3 individual signals, right? So gen, if I lock this patch and double click on gen, I can actually edit the patcher right here, is going to have 3 inlets and 3 outlets. So in 1, in 2, and in 3. These are going to be my X, Y, and Z positions. The inlets are going to be the initial positions of my particle. And then I'm going to have out 1, out 2, and last but not least, out 3. And these are going to be the X position, the Y position, and the Z position of this particle, each being represented as an audio signal. All right, well, since we are going to be implementing our algorithm in gen, let's actually cut this, open gen back up, and paste this here so that we can see our formula as we implement it. Now, one thing we need to think about is the fact that we are going to be using feedback. We need to use feedback on each step, on each sample frame. Each time passes by a single sample, our gen patch has to look at the previous step and look at the position of the particle in order to calculate the next position of our particle. Now, we can use delay, we can use some other means of feedback, but what I'm going to do here is to use an object that is specifically created for this purpose, that is history. History, as it says here, is a single sample delay allowing feedback connections. When history receives something in its inlet, it is going to send it out one sample later. So when we calculate our particle position, we are going to put it in history, and then it's going to send out that position during the next iteration. We have performed feedback. There are some optional arguments that we can give to history. First of all, we can give it an arbitrary name. Let's create 3 history objects. So history X, history Y, and history Z. Secondly, we can give history an argument representing an initial value, and let's just give it some random values as, the starting position of our particle. So 0.44 on the x-axis, 0.21 on the y-axis, and minus 0.56 on the z-axis. Just complete random numbers off the top of my head. Right, so these are going to go through our algorithm, and whatever the result is, we are going to plug this back into history. However, before I implement this algorithm, there is something else I want to solve, which is the ability to reset or set the particle position at any given time. This is why I have these 3 inlets here. I want to make it so that I can simply decide to start over. Maybe I messed up with my attractor, maybe it's too chaotic, maybe just for experimentation's sake, I just want to restart everything in a different position. I want to be able to do this using these inlets. However, if I am not doing that, I want the feedback to happen and continue, right? So I have 2 choices here. On each sample, I either reset everything using these 3 inlets, or I let my feedback system continue. And here is how I'm going to solve this problem. I'm going to use this mysterious object called a question mark. Well, it's not a question mark because it's mysterious, it's question mark because it's a ternary operator, right? It comes with 3 inlets. The first inlet is a condition to test. Well, it's expecting a value that is either 0 or 1. And if it is 1, if the incoming value here is 1, then whatever goes into the second inlet is going to come out of the outlet. However, if the first inlet receives a 0, then it is going to instead take whatever is going into the third inlet and send that out. And this is a way that we can accomplish what we want to do, right? I can create 3 instances of my ternary operator, and I can put in1, in2, and in3 in the second inlets, meaning that if the first inlet receives a 1, these values are going to be sent into history, and then we have reset the place. Then history, instead of taking the value that comes previously in the previous iteration, it is going to take these new values and it is going to put those values through the attractor. However, if these first inlets receive 0, I then want my feedback to take place. So whatever comes out of history should go here, and then from this outlet back into history. So how do I work with these 0-1 transitions? Well, I can simply define a new inlet in 4, so a 4th inlet, and this is going to give me, or I'm going to use this to send impulses in my gen. Single sample impulses. A single sample impulse is a single sample with a value of 1, after which it goes back to 0. So there's going to be this brief instant where this in4 is going to send a value of 1, meaning that my in1, in2, and in3 are going to pass from the outlet of my ternary operators, and history is going to give this value instead, starting things over. Okay, so then the 4th inlet, we need to use the click tilde object, which we can then trigger with a bang. This is something we are going to test a bit later. Okay, the stage is set. We can finally implement this algorithm. And this is actually fairly simple, right? First of all, let's define our constants, right? So param, short for parameter, and then 2 values, the name of the parameter and the initial value of the parameter. So param b 0.90. The cool thing about setting parameters is, 1, we can change these from outside of the gen patch or outside of the gen object, and secondly, we can actually now refer to b as a variable, as a value. So for instance, if delta x is minus b times x plus sine of y, I can type something like this in a new object box, times minus b. Normally, this would immediately throw an error, but because I have defined b as a parameter, this gen patch is going to know what minus b means. It's whatever my b parameter is, and it's the minus negative version of that. So let's calculate delta x. Delta x is minus b times x plus the sine of y. So I can create an object, sine, and then y. There we go. We have calculated delta x. Of course, as I've said, there was one more step, right? We had to multiply or divide this by a delta time value to determine the speed of our attractor. So let's set that or declare that as a parameter, param dt. And let's initially give this a very low value so that it is very slow, something like 0.001. And once again, I can just take my delta x and I can multiply this by delta t. Okay, and I actually just need to copy this collection of objects twice to calculate the y, delta y, and delta z. Because delta y is y times minus b plus the sine of z times dt. And delta z is z times minus pi plus the sine of x times dt. There we go. Of course, do I send these out? No. Again, remember what I said at the beginning. This formula is calculating the delta of x, the delta of y, the delta of z, as in the movement, the value that we should add to the current position of our particle. And what has the current position of our particle here? This history x, history y, and history z gives us the position of our particle before we started applying this mathematical formula. So what I'm then going to do is when I have delta x, I'm just going to take my x position and add that to my delta x. And I'm going to do the exact same thing with the other objects. Now you might notice that we are going into the spaghetti kitchen, as in this is getting very, very, very messy, which tends to happen if you are working with chaotic systems. Right, that is why I try to do my best and organize things neatly. But a nice trick you can do is to, well, on a Mac, hold Option, select several patch cords, in this case all patch cords that have to do with X, the X coordinate, right click, choose color, and then give it a nice color. So I'm going to make this red, I'm going to make the Y positions green, and I'm going to make the patch cords of the Z position a nice blue color. There we go. Now it's a bit more obvious what is happening in this patch, and we can read the signal flow a bit easier. All right, and these resulting values, the positions of our things are going out of here, but this is not it. We are missing a very important component here, the feedback, right? So whatever the result of this operation is, I want to take the new position and I want to plug that into the third inlet of my ternary operator. Right, so this is what is going to be sent to history as long as my fourth inlet is not sending me an impulse. And here it is, we have applied our chaotic attractor, I believe, if I have not messed anything up. And let's define some, well, we don't have to define the initial positions because we also defined those in the history operator, but just, you know, to make sure everything is complete, let's do something like this. Let's create a sig tilde object, which is going to convert numbers into audio signals. And then let's use a number box in order to translate these into audio signals and then into our gen patch. And now what I'm expecting from gen are 3 signals, each representing a single coordinate of my particle, X, Y, and Z coordinates of my particle. And again, if I start my audio contexts, well, nothing is crashing, which is already a good sign, but I'm not even going to plug these into my EasyDAC object just yet because I want to visualize what is happening first. And for this, I'm going to use the scope object, which is going to visualize an audio signal. If I create this, if I take one of these audio signals and put them here, let's set some random position, send an impulse. All right, there we go. Now we are having some kind of movement. First of all, it's not very smooth. Secondly, it is going out of bounds, as in it's going below -1 and below -1 and above +1, as it is doing this quasi oscillation. To fix that problem, the fact that it's going out of bounds, I'm going to take a very simple approach, and I'm just going to multiply the signal initially by 1, but then by another value that is less than 1 in order to scale it. There we go. And to make this look less jerky and at a better frame rate, I'm going to go to my inspector. I'm going to change this attribute, calc count, samples per pixel to display. And let's make this, instead of 256, I'll make this, I don't know, 10. There we go. And now you can see how this is moving. And as expected, yeah, it's completely random. There's some kind of pattern here. Maybe I can do something like this. I can take another signal, so the Y coordinates, multiplied by the same value, and put that signal into the second inlet of scope. And bam, this is going to give me a 2D representation of the incoming signals, where one is interpreted as the X coordinate and the second one is interpreted as the Y coordinate. So there we go, we have chaotic motion right here. This little guy flying around is our particle going through the chaotic attractor. Now we've defined some variables, right? So if I right click onto the first inlet of gen and select, let's see, DT, I can actually increase this to speed things up. And as I speed things up, look at what's happening. We do see some patterns emerge. If you remember the beginning of this video, you will actually remember that this is a pattern that we have seen in that web page. Right, if I keep increasing DT, it's eventually going to stabilize in a shape and it's going to break down. It's going to be a bit too jerky. If I go slower and slower, the pattern is going to turn into these very specific movements of a single particle. We can also mess around with our constant B. Again, right click on the inlet, choose B, go here, and instead of 0.19, I don't know, can change this value, and look, the pattern itself is changing as well. Which is cool and all, and you might notice that this is essentially a signal with values that go from -1 to 1, so it's a bipolar signal that is more or less chaotic, and this can be used for a lot of ways, right? So let's talk about actually sonifying this signal. The things that we can do, the list of things that we can do is infinite, or it's at least close to infinite. We can essentially use this for, I don't know, EQ sweeps or filter sweeps, or we can use this as an oscillator, we can use this to read a wavetable, we can use this to drive a granular oscillator, we can use this to drive an FM oscillator, we can do all sorts of things with this. I'm going to be showing 2 examples here, just as examples, and I want you to try different things if you can and if you're interested to sonify this, or at least use these signals in generating or manipulating audio in MSP. All right, so let's start with a simple example. What if I just try to play this out? Well, I'm going to create live.gain tilde to have some kind of volume control in case things get too loud or too quiet. And secondly, and this is very important, I'm going to create limit tilde with the argument 2. This is going to act as a peak limiter, and especially when we are working with chaotic attractors, things might get a bit too crazy, things might get a bit too loud, and please use this object in order to not damage your ears and your speakers and then get upset at this video afterwards. All right, now that we have taken our precautions, what happens if we simply take this X coordinate signal and plug it into our live.gain? All right, it makes a noise. It's not a very interesting noise, but the fun thing is going to happen once we start manipulating our parameters. And again, these are very crude sounds. These can be processed further by using equalizers and reverb and those kinds of effects. But notice how the shape of this attractor is corresponding very well with the resulting sounds. And again, if you messed with these parameters a bit too much and you want to reset things, you can just click this button right here. Fantastic. We can also play multiple dimensions at once, right? So I can play the X and the Y coordinates at once for a richer timbre. Cool. Now, another thing I can try is to play some kind of audio buffer back using this chaotic quote-unquote oscillator as a reading point inside that buffer. So let's set up an audio buffer. I'm going to create a buffer object using buffer tilde. I need to give it a few arguments. Let's give it a name. It can be and let's give it a file name, a file to load into this buffer initially. And let's use a classic anton.aif. Secondly, let's visualize this buffer so we can see the waveform. So we can use the waveform tilde object with the argument, with the attributes, buffer name, and then the name of our buffer, and here is our waveform. Now, to play this back, there are a lot of objects that can help you with playing this buffer back, but we are going to use wave tilde as our object, which is a variable size wavetable, right? It only expects the name of a buffer as an initial argument, so we can type in and now this is going to be the table position, or the position of our readback. It's going to expect a value between 0 and 1. The first inlet of wave tilde is going to expect a value that goes from 0 to 1, and as we go from 0 to 1, we are going to read this buffer back. Of course, instead of using a phasor ramp or a stable oscillator, we can also use things like our little chaotic attractor right here. So let's use the x coordinate, the x signal of our chaotic attractor to drive the readback of our wavetable. Once again, a very chaotic, a very noisy sound, but as we go down, we can see that the playback becomes a bit more predictable. I can even go slower. To have a very specific readback of the buffer. I can even make it so fast that it starts acting as a real wavetable, as in it is a wave that is oscillating in a very chaotic manner. Of course, there's a problem here, and you might be hearing those little gaps in our playback that is essentially turning this into some kind of AM monstrosity. That is the fact that this chaotic attractor it's bipolar. It goes below 0 and above 0. However, wave only expects values between 0 and 1. So when I take this signal, I can use the abs tilde object to get the absolute value of the signal, meaning that if I get negative values, they are going to be converted into a positive value. Let's hear it with the absolute value of the input signal. Alright, so some cool sounds right there. But there's one more thing I want to try. Right now we are simulating a single particle. And you might remember that most strange attractors, when visualized, are not comprised of a single point in space. It's usually hundreds or thousands or even millions of points going through the attractor. Now, it is very difficult to have millions of oscillators or millions of gen patches at once, but there is something we can try, which is multi-channel objects and multi-channel signals, which is signals that contain multiple signals inside, hence the name multi-channel. It's a signal that has multiple channels that is contained inside. Meaning we can, start a bunch of particles at different positions. We can read back all of those particles at once, and we can sound all of those particles at once, which should give us a much richer and a more interesting sound. So to begin with, I'm going to copy my gen patch. Secondly, I'm going to double click on it while it's unlocked. I'm going to go to the beginning of the object name, and I'm going to add 3 magical characters, mc dot. So gen turns into mc.gen. As you might know, a lot of MSP objects have multi-channel counterparts that is essentially mc dot, the name of that object. So mc.gen, since we have renamed an already existing gen patch, is going to have the exact same thing in it. That is on purpose. That is what I wanted to have. However, mc.gen can run multiple instances of this algorithm at once, and it's going to determine how many of these instances to run, depending on how many channels it is going to receive. Meaning, instead of using sig tilde to determine the initial position, I can use mc.sig tilde, and then I can set the amount of channels, the number of channels, by using the chance attribute. So I don't know, let's have, for instance, 50 channels. I want to have 50 particles at once. But of course, if we want to display the chaotic behavior of these particles, we need to make sure that each channel contains a different value. I want each of my 50 channels to have a unique value associated with it. And if I look at the reference of mc.sig, I will see that there is a message that relates to this problem, and that is called deviate. Deviate, the message deviate is going to generate a random value for each channel around a center value. For example, deviate 100 cutoff 1000 will generate random values for the cutoff attribute of the objects in the wrapper centered around 1000 Hz, around 1000 Hz, plus minus 100. This cutoff attribute that doesn't mean anything for us. I don't care about the cutoff. I just care about the value that I'm going to generate for the output, for the outlet of this object. So I can simply type in something like deviate, and let's say I want to deviate plus minus 1, and I want to start at 0. This is going to mean I'm going to receive values that go from minus 1 to 1, right? So 0 plus minus 1. And I'm going to send this message to all of my mc.sig objects. Secondly, I still need this click tilde object here. This does not need to be multi-channel because this is going to be uniform. I'm going to reset all the particles at once if that is necessary. All right, now let's see how this is going to look. I copied scope, but that was a bad idea. I should actually be creating mc.scope tilde to visualize a multi-channel audio signal. So let's see what's going to come out of the X and Y signals from our chaotic attractor mc.gen patch. All right, and you can see we're getting some movement here. We can do the exact same thing that we have done to the output of our gen tilde patch, which is to multiply the signal. So mc.multiplication times 1 initially, and then I'm going to again use a float number box in order to set this scalar value. If I increase this value, and if I click deviate here and then reinitiate the particle positions, well, look at this. This resembles the image that we have seen on the web page a bit more, I believe, because this is the sum of all the movements of all the particles. We can even copy our parameters b and dt and connect this to our mc.gen patch. Right, so now as I change b, you can see how this pattern is changing with it as well. It's really cool. I really like these complex patterns. There's just something magical about the chaotic nature and how it coalesces into this beautiful pattern. But you're not here to talk. You're not here to listen to me talk about chaotic patterns and the aesthetics behind it. No, we are here to sonify this. So let's do the exact same thing again. Right? Let's create. First, let's take the results of this and let's mix it down into 2 channels, because I don't know about you, but I don't have 50 speakers here, but I do have my 2 speakers. So I'm going to create mc.mixdown tilde. I'm going to give it 2 as an argument, so it's going to be mixed down to 2 channels, and I'm going to set the auto gain attribute to 1. All right, secondly, this is a 2-channel audio signal now, so I am going to use mc.unpack, and I'm going to give it 2 as an argument in order to receive 2 audio signals. So it's not a multi-channel signal anymore, it's a regular audio signal. And finally, I can take my good old live.gain, my limi tilde, and my easyDAC tilde objects. And then let's see what comes out. Well, right now we are not hearing anything because I imagine that this is too slow to be audible. Okay, so timeout. First of all, notice that the scope is lagging everything. At least I'm right now legit hoping that there's nothing wrong going on with the video recording, because if too many things are happening at once, MC Scope is going to struggle calculating and visualizing the position of 50 channels at once. So I'm not going to visualize what happens, but let's just listen to it. Alright, some really funky sounds here. It really reminds me of FM synthesis. Maybe we can visualize this by using mc.scope, but then use the 2-channel version of each signal. Something like this. There we go. Can make it a bit louder, I believe. Beautiful. Look at that deep rumbling texture. Sounds so beautiful, so chaotic, yet we can still hear the pattern in the sound right there. And finally, let's try to implement the wave tilde version of our chaotic attractor playback. So I'm going to do the same thing. I'm just going to create mc.wave tilde with ant as not any ant as an argument. I'm going to create mc.abs tilde. And when I take the results of my calculation, so after mc.gen, after mc.multiplication, I'm going to put in mc.abs here, and then mc.wave, and this should give me a nice result. A very granular texture. However, if we slow it down a bit, there we go, a bunch of cool noisy textures. So here you have it. The important point, the main takeaway for this video is the fact that these are just signals, right? We can use this in any way that we want. We can use this to drive the readback, the playback of audio buffers. We can treat these as quote-unquote oscillators. And as I've said a few minutes earlier, we can use this for the, we can use this like a low frequency oscillator. We can use this to modify parameters of all sorts of audio processes. No matter what we do, the result is going to be this chaotic yet strangely attractive texture that cannot be replicated by any other means. I hope this video has been useful to you, and thank you for watching.